Okay, so I'm going to talk a little bit about surface parameterization now. So just like curve parameterization, which would be, say, along one of these edges where you can selectively pick a point along that curve with a parameter, you can do that basically in two directions across the surface. This is usually noted as a U direction and a V direction of the surface, similar to like an X and Y direction of an axis. So I've drawn kind of a test surface, which was just a flat surface that I've turned the control points on and moved them around to sort of give it a stretched out shape so we can test on. And this is good to note because the original UV direction of that flat surface is still maintained despite pulling it around in three dimensions. So I have the surface and I've brought it into grasshopper. And I can show the dimensionality, or the parameterization of that surface in different ways. So there's a multi-dimensional slider that I could use. And I can get some isocurves. And I've reparameterized the surface so that it's between 0 and 1. And the slider is between 0 and 1 as well. And this basically makes the U and V directions the two curves. So along this curve in that direction and that direction are these different parameters. And I could take their intersection if I wanted to. And get a point at that parameter. And so that's the same no matter how I stretch the surface around. Those parameters get stretched around, but they maintain their relationship to each other. So I can use that in some interesting ways. I'm going to turn this preview off. So since the NURB surface sort of maintains the parameterization of the flat surface, all surfaces in Rhino are sort of built from this idea. So even though you have a sphere, it has a seam that can be unrolled into a flat surface. And so to show that out a little bit, I'm gonna make a test case. I'm gonna make another surface down here, a plane surface. Let's hide this. I'll take this plane surface and I'm going to populate it with points. Say 100 points. And I'm going to make a diagram that's called a Voronoi diagram. Now, for each one of these points, it makes a cell. And everything inside that cell is closest to this point with respect to all the other points around it. So these cells are not orthogonal to each other because these points are not. And so basically there's a line between these 2 points about the halfway point, and where those intersect creates that cell. So this is useful for any number of things, but it's used a lot in parametric design. I would say it's overused in parametric design quite a bit, but it's a good sort of diagram to show off the parameterization of the surface because it works in two ways. In this case, it's working on the flat plane of that 2D surface, or if I were to plug this surface into it, you can see that despite the surface and the points being in 3D space, it's still sort of building it along a plane, sort of a median plane of those points, but not on the surface. Now you can make a 3D Voronoi. but that makes a volumetric form in a similar way, because I have two of those, but they both work the same. So that's not making the cells on the surface either. That's making these three-dimensional cells along the same sort of principle. So neither of those make that pattern across the surface. So how could we do that? Well, since the flat surface and the three-dimensional surface share the same parameterization, we can make it on the flat surface and then map it to the 3D form. So as long as those parameterizations match, it should work. So what I'm going to do is I'm going to get the dimensions of this surface. One up top. Plug this in to our plane surface so it gets a little bigger. And make sure and reparameterize it. So both of these surfaces are between 0 and 1 in the U and V direction. And I'm going to populate it with the points and make the Voronoi diagram. Now you can see this diagram extends off the edges of that surface, so I actually want to set the plane surface as being the boundary as well. And I'll turn on these full names so you can see that a little better. So now that is just being mapped over that surface. Okay, and so for each one of these, if I want to draw this across this surface, which is disappearing on me, I need to get the parameter for each one of these curves. So I can get, let's say, explode these curves, which gives me the segments and the vertices. And if I had the parameters of these vertices, I could transfer them to the other surface and build these curves again. So I'm going to use a surface closest point. I'm going to take these points and this surface. So it's going to say what's the closest point on this surface to this point right here, which is basically on at the same spot, but it gives me a UV parameter. So if I evaluate this surface with this UV point, it should give me the exact same points I had before, as well as a normal direction, a U direction, a V direction, and a plane on there. But since those UV points are the same for both the flat surface and the curved surface, if I plug the curved surface into this, it also maps them to that. Now I want to make sure, okay, it's just going down past that. I'm going to change the visualization so you can see that a little better. Okay, so these are all mapped the same as this surface on this surface, but since the surface itself, the three-dimensional surface, is sort of stretched and pulled around, that's all pulling around with it. So turn some of this stuff off. Now if I rebuild those polylines, and you can see here that the tree structure is still the same as it was, so those polylines rebuild into that same cellular surface. They're not exactly the same shape because they're being stretched around, but they're the same topology, same number of cells, the same number of edges for each one. They're just mapped to the surface. And you can see in some cases, since the point location is far apart from each one of these polylines and the surface curves, it comes off the surface. Now I could increase that resolution by dividing up these curves and pulling them to the surface in the same way. But for maybe for this purpose it's fine. Okay, so let's use that to do something more interesting. Let's say get the polygon center point. I guess 3 different center points depending on the vertices, the edges, or the area. And then I'm going to actually evaluate that surface again. I want to take the center point, and I'll just pick one of these. And I want to evaluate this surface this time, the 3-dimensional surface, by the center point. And what that evaluation does is gives me that normal direction again, which I haven't used. But say if I want to build these into little truncated pyramids or some geometry in reference to the surface, I can do that. So I'm going to extrude to a point. And I'm going to extrude this polygon. To this point. So these makes these little pyramids along that surface. Let's turn the original surface off. And these points. So it increases the resolution, but then it also gives me some ability to make these little truncated cones. So let's say instead of just going to that point, I want to move this say in the normal direction. I'm gonna give it some multiplier, so I can say, okay, in that normal direction, then maybe 4 times the distance. To get these, I guess it's spiky inwards. Let's reverse it so it's spiky outside. Okay, so this is all starting to make some geometry from the surface. Now let's say if we can use some tools to adjust that. So we have our U and V directions. Those are vectors. Let's see if we can get an angle from the U direction to, say, the global X direction. So let's use this in our amplitude and see what that does. Now it changes it some, but it's kind of difficult to see what it's doing. This angle is just ever so slight. Around 2. Let's remap these so we can try to adjust it a little bit. So remap this number, get its bounds. Make sure and flatten it so that it has all the different versions. So it goes from 1 to 2 basically. And I am going to remap it between 0 and 1, or let's switch that and say between 1 and 0. So if it's closer to the X direction, it should be a higher number. And then I'm going to add a multiplier just so that I can, I guess I already had one down there. Just so I can show it a little more. Okay, so you can go ahead and see some of these in the middle are spiking up a lot more than the ones on the outside. Now I'm just using the U direction of this surface. I could break off that normal. Sorry, get the vector. Say maybe the vector of that could do some interesting things. Or actually, I'm just using the component. Let's just use the U direction. That seemed to be working fine. Now I'm using that U direction. I'm getting some differentiation in that surface. Let's visualize that a little bit better. Give it a color. Just a little too bright. Just for the sake of this tutorial, I'm going to use a custom preview that you guys might not have. Comes with another plugin called Human. But at least it shows the edges so you can see that geometry a little better. So that's the Voronoi diagram mapped to a 3D surface, sort of using the parameterization to give it some triangulated form. Now, we can also use a pretty standard method. If you're familiar with Lunchbox, you have a lot of different surface mapping panels to that. We can use a hexagon one. Now, in this case, it uses a very similar sort of process of surface mapping. Now I could map it directly to this 3D surface. It can do that with this component, but it's basically going through a similar sort of process of finding the UV coordinates of that surface to then create this pattern. If I follow the same sort of logic that I did for this one, maybe I add a few divisions to this. Turn that down a little bit. Let's see what that looks like on our surface. Hopefully it doesn't crash everything. You can see we're getting some pretty complex geometry. Our little pyramids are updating for the UV coordinates. And it's starting to do some pretty interesting things. So I think that's it.